Hey everyone, Zeke here with 5 of rotational motion, and I'm going to be giving you guys a couple of minutes so we can have more of you join. And for those of you who are on here, can you please vote in the poll that we have up just so we can get your responses on what you guys are wanting to go over tomorrow? And that is also a reminder, today is the last day of just like straight content review, and tomorrow we're going to be doing review over what you guys feel like the worst on. Also, unfortunately, yesterday's first recording that was over momentum was lost. So we will be covering some of those topics again tomorrow. And if there's anything specifically out of that unit that really tripped you guys up, put those down in the chat too, so we can make sure to heavily go over that. Okay, so now we're going to go ahead and get started. So let's go to our next slide. So you guys have already seen this 3 other times, but just to make sure that our schedule is clarified, on May 6th, we went over units 1 through 2. May 7th, we did units 3 through 4. May 8th, we did units 5 through 6. A reminder that unit 5 recordings is lost, so we will be going over that again tomorrow. And more specifically, if there's anything that tripped you guys up out of momentum, put that in the chat. Today, we're going to be doing Unit 7 and a unit wrap-up if you guys feel like you want to move on from Unit 7. And then tomorrow will be our grand finale, the last day before the AP Physics 1 exam. And we will be covering all the different types of free response questions and be doing a more broad overview of anything that you guys struggled with out of the units. So now I'm going to introduce our host again.
Hey guys, it's Anastasia here, and today I will be in the chat and I'll be answering your guys' questions.
Hello, it's Liliana, and I will be doing some FRQs and MCQs today with you guys.
Hi guys, I'm Shagun. Today I'll be going over mainly rotational inertia, translational kinetic energy, and then we'll be going over some fun MCQs and FRQs.
Hey guys, my name is Tammy Matthews. We're going to be doing a simple harmonic quiz if we get time. And yeah, I'll be in the chat for the bigger part of the evening.
And again, I'm Zeke. I'm going to be starting us off today with our intro slides, and then I'm going to be introducing the topic of torque and angular momentum. So let's go ahead and move on to our next slide. So just a reminder again to follow at ThinkFiveable on social. They got TikTok, Instagram, YouTube, and they're on LinkedIn. So today, night 4, we're doing unit 7, and we're doing a lot of practice problems and FRQs over this unit since you guys have said you struggle on it a lot. So our agenda for tonight is doing our welcome, which we're doing right now. And then we're going to jump into unit 7, which is torque and rotational motion. Quick reminder, it's 12 to 18%. Then we're going to do some practice problems and then extra problems from night 2 and 3, if time allows us. And then we're going to do a wrap up. So just a reminder on how to make the most of cram finales, okay? So notes, right? They keep you active, but don't try to write down everything, right? Write down things that you struggle with, that you know that you don't really know. And then reminders, so try and do some mnemonics, questions, study the do list. So if there's something out of a specific unit that you really know you're not good at, put that on a to-do list so you remember to do it. The Cram Hub, it has all of the slides, the review packet, and replays for you. Follow along. Just a reminder too, we have more AP practice problems in that Cram packet. So when you're done, make sure that you're going and doing those as well, because if you're struggling on some of those, we can go over that tomorrow. The group chat, right? It's for sharing tips, tricks, and to participate when we ask questions. This is super important. I really like the community that we have here, and it's also nice that you guys are able to kind of share ideas with each other and sometimes even resources. The question and answer tab, right? It's for asking any question, and you can check the comments for answers for short things. But if we think it's something that needs more of an explanation, put it in there and we will cover it like on the main slides. And then just a reminder also, yes, we will be taking breaks, and yes, the replay will be available immediately after the event. Okay, let's go to our next slide. So we have some community agreements here, right? Be supportive, so let's lift each other up. Don't be mean in the chat if someone doesn't know something, and be nice to the host, okay? 2, be patient. So we have 5 nights together. Now we have 2. This is one of our last 2 nights, but we're really trying to make sure all of you guys understand it. So we don't want to move on if only 2 of you guys understand something and there's 100 of you on here. And 3, be kind. We're all real people. So don't be rude to us hosts unless, you know, y'all don't want a good review. That's all I'm saying. Okay, so let's move on. Okay, so another thing, you guys can win $100 by sharing your cram experience. So you can post about your cram experience on TikTok or Instagram. You can use the hashtag #5ablecrams and tag @ThinkFiveable in the post or caption. Make sure your account is public and you follow @ThinkFiveable so that they can actually see your post. And then you win by making Fiveable laugh out loud, right? Or getting a ton of views. Several students will win each week. So that means that if 5 of you guys do one of these, there's a chance that a couple of you could win. And then we'll select winners throughout the next 2 weeks of cram finales and notify you via DM from our official account. Okay, let's move on. So now we're going to jump right into Unit 7, which is torque and rotational motion. So let's start off with rotational kinematics. This is why kinematics is honestly really important to know, is because you're basically doing the same thing except changing variables to apply to rotation. So it measures rotational motion in an inertial frame or reference, right? It always uses radians to measure angle values, and you replace with the matching linear variables and use as normal in kinematics. So what that means is it's basically the same kinematic equations that we used before from Unit 1, But now we're just replacing them with units that make sense for rotational motion, right? We also have a diagram in the top right corner. It's pretty important. Remember that your arc length is going to equal the radius. And we have that depicted up above. And then we have some quantities, the linear term, the rotational term, and then the rotational equation, right? So for quantities, we have displacement, velocity, and acceleration. So your linear term for displacement can be x, y, or z. It depends, but typically it's going to be delta x for linear. And then your rotational term for that is going to be theta, because that's how much your angle is changing. And then for rotational equation, it's going to be x equals the theta multiplied by radius. That makes sense because that's how much we're rotating, we're changing, right? For velocity, you can see it a couple different ways in linear terms. It can be like Vy, Vx, V sub I, V sub F. Your rotational term is going to be W, and your velocity is going to equal W multiplied by the radius. For acceleration, you can also see it depicted in a couple different ways for the linear term. Once again, it can be like AV, AY, A sub X, right? The rotational term is going to be like a fancier looking A. I can't remember the exact term for it. It's been a while, but know it when you see it. And that is going, or that acceleration is going to equal the acceleration multiplied by the radius. So let's move on to our next slide. So now let's move on to torque. The big thing here is that torque equals the radius multiplied by the force multiplied by sine of theta, okay? So torque is the rotational equivalent to force. So when torque is balanced, objects are in rotational equilibrium. And torque is going to depend on three things. It's going to depend on the distance from the pivot point, which is the radius, and the force magnitude, which is going to be depicted as the F, and the direction of force, which is going to be your sine theta. Only perpendicular parts of force to the pivot point are effective for torque. And counterclockwise movement is considered positive unless it tells you otherwise in your question, which I have seen. So don't always assume that. Your question should tell you, but if it does not tell you which direction is going to be positive or negative, just assume that the counterclockwise movement is going to be positive. Let's move on. So angular acceleration is going to equal the sum of torque equals the moment of inertia multiplied by the acceleration. So moment of inertia is the rotational equivalent to mass. So this measures resistance to rotation and distribution of mass. And a point mass uses the equation inertia equals the sum of mass multiplied by radius squared. You will not need to derive other moment of inertia equations on the Physics 1 exam. So that's important to know, right? So you don't have to know all these other different equations. You just have to know that one. And angular acceleration, the angular acceleration equation is the rotational equivalent of Newton's second law of motion. Okay. Oh, can we go back real quick though? Sorry, I just want to say that this diagram is really important because you will see a lot of questions like that, honestly. It's going to ask you if, you know, is your moment of inertia going to increase when you move your mass in or not? And that is especially going to apply to angular momentum, which I think we're about to cover. So we can move on now. So, yep, here we are, angular momentum and torque. So, describes the amount of rotational motion of an object around a particular axis. And it's going to be a vector quantity. So the product of an object's moment of inertia and its angular velocity is going to be the angular momentum, yeah. So the equation for angular momentum is L equals I multiplied by W, which is the angular momentum equals inertia multiplied by angular velocity, where L is the angular momentum, I is the moment of inertia, and W is the angular velocity. Angular momentum also equals mvr, and angular momentum is conserved in a closed system, meaning that it remains constant unless it's acted upon by an external torque. This is also so important on multiple choice questions. I've seen so many that trip people up because you have to really think about your system, and it doesn't matter what's happening in the system. As long as it's in the system and nothing external on the system is acting on it, your momentum will be conserved. So if an object experiences no external torques, its angular momentum will remain constant regardless of any changes in the moment of inertia or angular velocity. This is something to literally ram into your brain. This is the most common type of questions I've seen on torque or in Unit 7 in general. And torque is a physical quantity that describes the rotational effect of a force on an object. So let's move on to the next. Oh, let me make sure in the chat real quick. Are we given the orbital equation, and how do we prove it if we're asked to? I don't think I've ever seen that. I don't think you have to prove it. In reality, the only time that I've seen stuff that even involves like orbital stuff is going to be like planets and satellites, or like planets in general. And the only ones I've seen are when angular momentum is going to be conserved, and you just have to think about how angular velocity and inertia is going to relate to like kinetic energy and potential energy. Okay. And we can try and get some practice problems for that tomorrow, or if you don't feel like you're that prepared after tonight, just put that back in the chat. Okay, let's move on. Wait, hold on. Could you explain the external torque in closed system again? Okay, so this is so important. Like I said, this is probably like the biggest thing on there. So if you have a closed system, right, you have to know that no matter what, your angular momentum is going to be conserved. So it doesn't matter what's happening or what you think is going to change it. It's going to be conserved. It doesn't matter where your mass is changing or what's happening. I see students get tripped up about that the most. But when there's an external torque that's acting on a closed system, that means that angular momentum will not be conserved, because now you have a force that's acting on it, right? So a common example I've seen is we have one disk that's rotating, and so the angular momentum is conserved in that system. But whenever you drop another disk on top of it that's not a part of that system, angular momentum will decrease, because now that torque from that disk is exerting on that system beneath. A force is not a torque when it's acting perpendicular to the position vector, right? When it's acting perpendicular, typically it is. I mean, a lot of times when you see torque, that's really what it is. It's perpendicular. I mean, a torque is a force applied on a radius from an axis. Yeah, it is. But keep in mind, if your torque, I'm trying to figure out exactly what you're trying to say, but let's take this example, right? If I have this bar right here and I'm exerting a torque like this, nothing is going to happen. But if you have it perpendicular like this, that's what will cause it to spin. So that's another important thing that I see in practice problems, is if you have a torque right here or right on the fulcrum, nothing will happen. But if it's anywhere else, things will happen. Okay, so now let's move on. So now we have conservation of angular momentum, which is kind of what I was just talking about, right? So the law of conservation of angular momentum states that the total angular momentum of an isolated system remains constant, provided that no external torque acts on the system. So angular momentum can be transferred from one part of the system to another, but the total angular momentum of the system will always remain the same. This is what I was talking about that a lot of people get tripped up on. Just remember that no matter what, if it's a closed system and there's nothing acting on it, angular momentum will be conserved. So you see that as your angular momentum is constant because remember big L equals angular momentum. So big L is the total angular momentum of a system. Some examples of this include a spinning ice skater will spin faster when she brings her arms closer to her body because of the conservation of angular momentum. When she brings her arms in, she decreases her moment of inertia, which causes her angular velocity to increase, which overall conserving the total angular momentum of the system. That's because inertia is mass radius squared. So when she's bringing the mass of her arms in and angular momentum is conserved, she'll start to spin faster because her moment of inertia just decreased. And because of that, our angular velocity will have to increase. So also keep in mind, inverse relationship between the two of those. Something else I want to add, that will relate back to like the orbiting stuff. If you have a planet and you have a satellite going around in like an elliptic shape, right? The farther it is, the less angular velocity, right? So that means that your kinetic energy is going to be less. But the closer you are, actually, hold on, y'all. Let me not get this so bad. Okay. Yes, the closer you are, the greater kinetic energy you'll have, but the farther away, the less kinetic energy you'll have. Okay, let's move on. Wait, the farther, the less linear velocity, right? Yes, I think we're going to cover that, though, in the next slides. And yes, do not depend on formula sheet, y'all. Okay.
All right, thank you, Zeke. You did a great job. Okay, so we're going to be going over everything that you need to translate over from rotational motion to linear motion to rotational motion. So the number one thing I want you guys to type it in the chat right now is please, please, please do not memorize them. Literally say, I will not memorize these equations. The first three kinematics equations, there are all on your formula sheet. And then you're also given the translation or how you can convert between, for example, omega and velocity, or angular displacement or theta and position, or angular or alpha and acceleration, right? So you do not need to. There we go. Thank you, Ben. Okay, I see all these comments. There we go. Okay. Okay, someone already, well, thanks for memorizing them, but there we go. We're not going to memorize them. You can easily convert for them. Remember, the main thing that's going to be on your formula sheet is velocity is equal to r omega. So therefore, you can literally convert from one thing to the next by just one thing, and that's your radius. So your radius is your key thing. If you're given a radius problem, if you're given something that's rotating, if you're given a disc, a hoop, a sphere, and you have to convert from kinematics to rotational equations, you have to, you just need your radius. So essentially, just to go over them really quickly, our first kinematics equation on the top can be translated. It's literally the same exact thing. So if you know what is analogous to what, and I'm saying analogous because it's not the same thing. So if you know that displacement is the same thing as angular displacement, which is theta, your angle, velocity is omega, alpha is acceleration, you can do the whole switcheroo really quickly. And if you memorize them, honestly, that's more work for you, and that's not going to help. So it's really important you just keep these in mind. And again, you can always switch back and forth due to the radius. All right, next slide, please. Oh, what does the sign sigma before? Okay, yeah, I'll get to that. But basically, sigma just means summation. So if you guys remember from the center of the mass equation, it's like you're summing up all the, that's how you're summing up all those values together, and that's what summation is. I don't know if you guys have taken calculus yet, but an integral is basically a summation because you're summing up all the different types of tiny values together to make one big area. So summation is just you're adding all those together. Yeah, you don't have to know what it means. Just know that, oh, if I'm given like two different spheres and I have to calculate their entire rotational inertia, that means you're summing the individual rotational inertias to get the one in total. All right, next slide, please. Okay. Okay, I apologize in advance because some of the slides will have some fun cringy wording, which I could not help myself with. So just a fair warning on that. So, okay, rigid bodies. What are rigid bodies? Rigid bodies are essentially any object that does not deform. So this pencil, this calculator over here, I can't break it, it's not deforming. That means I know it can rotate, and whichever way it rotates, so it has torque, and I can move it, so it has linear acceleration. So for a rigid body to be in static equilibrium, the object must be in both translational and rotational equilibrium. Now, what are those? So translational equilibrium essentially means that you have no linear acceleration. So if you think back to Newton's second law, force equal to mass times acceleration. So there's no linear acceleration. That means our net force is zero. And the same thing goes for rotational equilibrium. Tau, which is a sign for torque. Essentially, if you have zero torque, or if you have zero angular acceleration or zero alpha, that means you have no torque. So if you can see in this little diagram over here that I have, I don't think it's that clear, but essentially, if the force is just like, I know some of you guys had some questions on that, on the perpendicular and what's the deal with the angles. So you don't need to know this for physics 1 especially, but just know that whenever you have like a dot product, that or whenever you have something to do with cosine theta, if you just think about how cosine theta works, it's the opposite of sine theta, right? So cosine theta means my bad, let me just rephrase a second. So let me just go back to the work equation. You know that work is equal to FD cosine theta, or it's actually like the definition you're going to see is F and the dot product of distance. So whenever you're going to see like a little dot product, that means it's cosine, and cosine essentially means that cosine 0 is equal to 1. Whenever you're that means whenever you're parallel, so you have no angle, that's when cosine equals 1. That's why work is force times distance parallel, because you're doing work parallel to the distance you're moving. However, torque is the exact opposite. Whenever you see an X, which is basically the cross product means sine. So the official definition of work is R cross F. So in physics C, just a heads up, you're going to actually have to take the cross products. But in physics 1, it's simply the R cross F is equal to force times the radius times sine theta. And if you think about how sine works, sine of 0 is 0. So that means anything parallel. So for example, if this is my beam and I have this pencil and it's like this, there's no angle between them. So therefore, the pencil does not have any torque. It's not exerting any torque on the beam. However, if I make a 90-degree angle, we're going to pretend that's exactly 90, then that means that I'm exactly perpendicular, and sine of 90 is 1. Therefore, you will have torque only when it's perpendicular to the force, or again, if there's an angle, then you just take the sine of that. All right, next slide, please. Yeah, okay. I'll just go through. All right. No, you do not need to memorize the center of mass formulas. They're on the equation sheet. Yeah, I'll be going over the chat in a second, but thank you to my host for looking it over. All right, so I know Matthew already said this in the chat, but thank you for stealing my spotlight again. When I learned the pencil rule, I first didn't know what it was exactly, and then when I learned it, it's been helping me so much. So I want everyone to just take like 2 seconds and get a pencil wherever you have it, and then I'm just gonna show you how to do it, and then we're gonna do a little example problem. But essentially, what the pencil rule is and what it's used for, it's so you can find the direction of the torque. So a lot of times in your FRQ questions, they like to have like a little check mark and a checkbox that says, oh, like what's the direction of this force? Like what's the direction of its torque? And it's going to be like clockwise, counterclockwise. So just remember that unless if stated otherwise, counterclockwise, which is that way, is going to be your positive direction, and clockwise, which is the way we're used to, is negative. So essentially what you do is that you hold your pencil horizontally like this, and you're going to place your pointer wherever the pivot or the axis of rotation is. So usually in a beam, it's at the center, because the weight of the beam is you draw your free body diagram with the weight going down exactly at the center. I'm just going to put my pointer here. And then again, this is really important. You have to draw your free body diagram. So you want to see what force, what direction a force is exerting torque on this beam, right? So you need to know the direction of your force. If it's normal force, it's going up, gravity is going down, tension is going up. So just know the direction of your forces. So for example, let's deal with like a normal force that's going like up over here because there's some like mass on it. So essentially, I'm just gonna move my hands a little bit. If I know that, so my mass is over here and the normal force is going up this way. So what I'm gonna do is I'm gonna take my pointer or my other finger, whatever. You're just gonna move in that, remember, you're on the side of that mass, so you're gonna push your pencil up. So now I know that the direction my pencil is moving in, that is counterclockwise. So now I know that this upward force on the left side of my beam, on the left side of the center of axis, is moving in a counterclockwise position. However, for example, if I moved downwards, I'm going in a clockwise position. Did I do that right? Clockwise. No, that is still also counterclockwise. So yeah, just know exactly like what you're defining as positive and negative, so you can be able to understand where your torque is going. So we're just gonna do this really quick example over here. So pretend this is a really nice drawing of a beam and it's like completely symmetrical. So whoa, the light's not okay. Yeah. So this is your axis of rotation, and I don't know if it's flipped in the mirror, but my I have a downward force that's on the left, right. That's on the, it seems like it's on the left side of my beam or right side of my beam. Let me just check really quickly. Oh, thank you, thank you. I appreciate the drawings. I don't know, was this left or right? I apologize. I actually have to use my left and right hand for this. So this is right side. Okay, wait, left. It looks like left for you guys. Okay, we're gonna look on left on that side. I'm actually a dancer, so if I don't know my left and right, that's bad. Okay, we're just gonna assume there is a downward force on the left side of for you guys. Yeah, okay. So downward force, left side of your axis of rotation. Let me know which direction you're going in. Let me practice that too. Yeah. Also, whenever you're like, you can write either positive or negative. Just make sure you're like what I did for my FRQs last year. I just like specified in like I made like a key box and I said, oh, by the way, counterclockwise is positive, that is negative. But yeah, you guys are right. It is counterclockwise. This is gonna might appear in the opposite direction, but left side, I'm pushing up. Oh, nice. It is counterclockwise. So all right, good job. Hopefully that that's a really important rule. It helps a lot. It's nice to have. All right, next slide, please. Oh wow, okay, I had another practice up. It's all right. We can do another practice. We love the pencil rule. So really quickly, let's look a rapid round. So just calculate the direction of each of the forces and drop your answers in the chat. So A is going this way, B is that way, C is that way, and D is upwards as well. So just in the chat, just write A positive, B negative, 0, Z for A, B, C, and D. They're not all equal in magnitude, but I don't think that matters. Well, it doesn't say anything about drawn to scale, so we can assume. Yeah, Emma, we can definitely go over them. Oh, I like the answer nowhere. Okay, wow, you guys are actually fast. You took the meaning of rapid round to your heart. I appreciate that. No, it's all right, Ben. It happens. Okay. All right, yes. So you guys are right. So beginning A is parallel. So you guys all caught that. That is 0 torque. B is positive. It's counterclockwise. C is also counterclockwise. And that's kind of, and then you can see how that really makes sense if B and C are the same because, oh, sorry, I meant, yeah. There are 2 pivot points. No, there's only one. That says A. Yeah, that's a dashed line. And B and C, you can see they're on opposite sides of your axis of rotation, but they're different sides. So it would make sense by like logical thinking that they have the same rotation. And yes, D is also positive. All right, good job. That was pretty fast. I like that. I like the rhythm we're going. All right, next slide, please. Okay, so the most important rule of torque besides conservation of angular momentum is that the sum of all the forces that are going negative or the clockwise torque is equal to the sum of all the forces in the counterclockwise torque. So essentially, if your counterclockwise torque and the clockwise torque are all the same about any pivot point, your object will not rotate and hence you will be in rotational equilibrium. Now, a lot of people get tripped up because they think that torque and force can be like as if you can prove one, you have the other. So sometimes you will, but you have to check sometimes in diagrams whether you might have rotational equilibrium, but you might not have translational, and it could be the exact opposite. So whenever in any FRQ, MCQ, you're given this question where you have to check whether your beam is in rotational or translational equilibrium, just check both. So we're gonna do a little quick break. Not break. We'll do that later. But just I don't know if you guys can see it that well. If you can't, just look on the slides. That's in the Cram Hub. But essentially, I want you to calculate. Check that the following object, this beam over here, is in rotational equilibrium and translational equilibrium. So the best hint I would say is that use both your Newton's laws analogously for both rotational and translational. Oh, your pivot? Okay. This is a good question because in beams they're not going to tell you, but you're going to so for any beam, your pivot will if not else noted, it's always going to be at the middle. So what you have to do is actually calculate the entire distance of your beam and then find where that middle point is, and then you have to take the distance or the radius from each of the forces to the middle of the beam. Just remember that in total. Oh, and now yeah. So yeah, I meant like similar. You're gonna see that a lot like in physics videos where they're just like, oh, torque is like analogous to like force. Don't worry, we'll get a break soon. We're just a little early. Actually, I guess I didn't see that dot there. I thought it was like a non-force. I guess since A has no force there, that is a pivot point. But if you guys already started, okay, yeah, my bad. That's a tip you would say for later if there was no pivot point, but good catch. I didn't see that point either. It wasn't that big enough. But yes, A is actually the pivot point. Although I don't know why they didn't dot it, but it's okay. Let me check. Yeah, my bad. It is at point A. Yeah, I apologize for that, guys. I didn't see that dot. All right, let me know when you guys are done, because there does seem to see a little confusion on the chat. Part of it I will say is my fault for not seeing that pivot point before, but if you use pivot A, okay. All right, so let us, okay, I see some people not getting translational. Okay, no worries. So essentially, the way how you solve the answer, just to preface, is that it is both in rotational and translational equilibrium. So let's start with rotational equilibrium first, since you guys seem to have gotten that. But essentially, if you look at the diagram, use that pivot rule by your pencil. Remember, your pivot's at A. Then you have to equal all your counterclockwise forces to your clockwise forces. So the two upwards forces are 12 newtons and are 8 newtons. Those are our counterclockwise forces. And the downwards force is our clockwise force. So essentially what you would do is the 12 Newton force is exactly 1 meter away from the pivot point. So we do 12 times 1. And then essentially you don't have to worry about the sine 90 because we know they're all perpendicular. And then so 12 times 1, you would add that to our force all the way from to the end, which is exactly 6 meters away from pivot A, because the board is 6 meters away. So 12 times 1 plus 8 times 6, that is 12 plus 48, which is 60. And then you equal that, or if you're just finding the net torque, you can subtract that from our downwards or our counterclockwise force. And that is 20 newtons times, or negative 20 newtons, you could say, times 3, because it's 3 meters away. So 20 times 3 is 60. So if you have 48 plus 12 minus 60, that is 60 minus 60, which is 0. So since we do get 0 Newton meters, that's the units for torque. We do have the object in rotational equilibrium. And now let's go to translational equilibrium. So this one is a little trippy, but it's actually simpler than rotational equilibrium. Rotational equilibrium. And that's because you have to go back to our best friend, force equal to mass times acceleration. And all you're doing is summing the forces in the y direction, because you can see there's no forces acting in the positive or negative x direction. But if you sum of the forces in the y direction, we have 12 newtons going upwards, 8 newtons going downwards, and 20 newtons going downwards. So if you have 12 plus minus 20 plus 8, that's 20 minus 20, so that's 0. So the object is in translational equilibrium. The 6, it's 8 times 6, because 6 is the distance from 8 newtons to the pivot point of A. So that's 6, and then 8 is the force that goes up. Let me see if there's any other questions. Okay, do you want me to explain it again? How can you tell if you add the distances labeled or they're just labeling each part? Yeah, it's not drawn to scale. Just remember this. Could this be written out? Yes, if you look on the next slide, Juliana, I think it should be there. or it's not. I think you might have to X out of the slideshow and go back to see if it's there. Can you please go over on who would we would find the linear motion? Okay, so let me just look. This is more drawn out, so it's easier to see. But as you can see, where the top part is, thank you, Juliana, for the translational motion. Translational motion essentially is just mass times acceleration. So you're just looking at all the forces that contribute to linear acceleration, and that is just our Newton's second law of motion. So therefore, you don't care about the radius or how far it's away from anything. It's essentially just you're summing all the forces in the x direction. This is dynamics. So you're doing 12 minus 20 plus n. So you want to make sure whenever it says linear acceleration, linear motion, upward, all the upward forces are 12 at 8. The downward force is 20. So you have to create your free body diagram, whatever you can do to help yourself, but you have to make sure that on the beam, you're labeling the forces that are going up and down, and please write their magnitude. 12 is not negative because 12 is going upwards. So the two forces that are going upwards are 12 and 20, and then 12 and 8, and then 20 is one that's going down. And then if you look at the torque one, it's a little messy here because my writing, I don't have like the stylus. But essentially, you're just doing summing all the forces of the torque, and I put my counterclockwise as positive and my clockwise as negative. So it's just 12. 12. I'm starting with the upward force. If I look at my thing, upward is going counterclockwise, so that is 1 meter away. Then I'm subtracting the 20 meters, which is 3 meters away, and that's going in the opposite or clockwise direction. And then my 8 newtons over here, it's going upwards. So that is my counterclockwise direction. And you have to multiply times the correct distances. So some of you are asking, if you go back to the diagram, Juliana, in the previous slide, might not be the most, well, it is pretty clear here, but it'll always be clear. The distances are exactly representing the distance from, for example, that if you look at the first distance of 1 meter, that's explicitly telling you that, okay, this force is 1 meter away. But then they're not going to always say, they're not going to label out like 1, 3, 6. They're going to just tell you the distances between, that are spaced between, two forces or two different bodies of mass on your beam. So therefore, you will have to do a little addition, subtraction to see where exactly your point or your mass is in relative comparison to your pivot. Okay. All right. Hopefully, that was a little tricky problem. Just because it asks you for both, so it can trip you up because you think you guys know like rotational session and the rotational motion, and then like you forget like the easy things in translational. That happens all the time. Yes, and we will go over linear acceleration, translational acceleration, all of that. And yes, like Juliana said, when an object is in equilibrium, your pivot point does not matter. You just know that both wherever your pivot point is, clockwise and counterclockwise, those forces will be 0. All right, next slide, please. Okay. All right. So this is like the previous explanation said from our previous example. You will sorry about the cringiness again. I like the top of it, but essentially your force is equal to mass times acceleration. Here brings the equivalent in rotational motion, and that is because the sum of the forces of your torque is equal to rotational inertia times your alpha. So you can see if you just think about this analogously, that the force is analogous to your torque, even though they're different quantities. You can think of it as kind of the same thing when you're comparing linear and rotational motion. By that definition, you know that angular acceleration or alpha is analogous or proportional to your linear acceleration, and therefore mass is going to be proportional to your rotational motion. Now, please do not think that, oh, just because I see mass and rotational motion, rotational inertia, it's the same thing, because the two are very different and have very different properties, especially rotational inertia. But you can just think of them in this scenario like, okay, I can see what property goes with what property. So this is a super important equation of rotational dynamics, because now, before you knew one definition of torque, which is torque is equal to the radius times the force, or RF. Now you know that torque is also equal to I alpha. So whenever this happens way too many times, whenever you're on a free response question, you're always going to be given enough information so you could calculate 3 of these 4 values, so I, A, radius, or force, and then you will have to eventually plug it back into this equation in order to solve for the 4th variable. Yeah, okay. Are most bodies rigid for torque? Not really, but the ones that are not rigid will not be covered. But yes, please remember this. Actually, it's on your formula sheet as well. But you do have to know that whenever you're given, for example, force and the radius, and you're being told that, oh, this sphere has a rotational inertia of like 2/5 mr squared. What's the angular acceleration? You know how to find it, but it's not going to be always that easy. Sometimes you're given like the velocity, right? The angular velocity, which is omega, and then you're going to have to use some kinematics from those kinematics equations we saw before, and then you find you use your kinematics equations to find alpha, plug that in, do whatever you can, but you're going to have to, just like you do with dynamics, you're going to have to relate these equations together. Yeah, it's mainly just applications. It could be okay, let me look at this question. Can I use the equations for rotational and translational motion interchangeably? I always get confused when a question asks for a translational value. Yes, well, not in the sense that you can use it completely you can convert between the two. So yes, omega is equal to V over R, because our velocity is equal to the radius times your angular velocity. So whenever you're given equations for example, the translational value, if you're given the radius, you can convert into your rotational value, but you can't just like substitute. For example, if you're given linear acceleration, you can't substitute that in for your angular acceleration. You do have to convert with your radius. Okay, hopefully that answers your question. I'm just going to go over some Q&A. Oh, what is the difference between rotational and translational equilibrium? Okay, again, like you want to think about this analogously, but you don't want to think of them as the same thing. So rotational equilibrium is when the sum of the torques equals 0. So that means that you have no angular acceleration. So that doesn't mean that you don't have no motion. Remember Newton's law for first motion? You can still have a motion, which can be appear in the form of constant velocity. So in this case, you can have a disk spinning at constant angular velocity. But since velocity is constant, that means you have no acceleration. Your velocity is not increasing by any amount at any time. So therefore, that means you have no acceleration, no angular acceleration. So therefore, you have no net torque. And that is rotational equilibrium. And you find that usually in most cases by in those beam cases by using the R cross F formula and being able to sum all the forces that are clockwise and counterclockwise. And then translational equilibrium is the exact same thing, but in linear acceleration. So for example, if I'm running at like 5 meters per second, and I'm only staying at that speed and running at 5 meters per second, that's a pretty fast time. Then I'm not gaining any speed because I'm keeping that speed. So I'm running in constant velocity, and that's 0 acceleration. So translational equilibrium is zero acceleration. So you have 0 net force. Remember, it's just 0 in both cases, and your quantities that contribute to your force and torque being 0 are your linear acceleration and your alpha or angular acceleration. Can we talk about when we have multiple point masses and different axes and we have to rank each moment of inertia? Yes, I do think we have an MCQ coming up that's similar to that, but multiple point masses. So I'll be going over this really quickly, but you're gonna have to memorize that the rotational inertia for any point mass is mr squared, and then essentially what you mean by different axes is that you're going to be at a different distance. You're going to be at some sort of distance from either the x-axis or the y-axis. Correct me if I'm wrong for any of the other hosts, but I think for physics 1, you will not have to do double axes. Like you don't have to calculate the moment of inertia for like or the center of mass from an x-axis and a y-axis. It's always, oh, how much are you away from the center of rotation? And then you're going to have to rank each moment of inertia based upon your moment of inertia coefficient. So essentially, you're going to be given all this. You don't have to memorize, but if you have like a sphere and a point mass, a sphere has a rotational inertia of what, like 2/5 mr squared, and a point mass has mr squared. However, your sphere could be super far away or super close to your center of rotation, and the point mass could be far away. So you're going to have to plug in those values of, for example, 2r and r, no matter whatever that value they give you of their radius, in order to determine, okay, which one has a bigger value. So there's a lot of fractions involved, but that's how you would have to rank. Yes. Okay. Let me look at some more Q&As. Okay, this is more like study skills, but you guys suggest taking a full-length practice test the day before the test. Okay. This is, I would say no, not a full-length physics exam, because I would suggest that do the problems like literally today, because it's the day before the exam. Write down, oh yeah, you have 1 day left, so tomorrow's your last day. So today, write down all the topics that you struggle in. So whether it's energy or simple harmonic motion or momentum, write down those topics, and then only whichever sources you have. We suggested a lot on our Cram Hubs, but only do multiple choice or FRQ practice questions on those topics. Now that doesn't mean you like completely forget about the other topics. You can practice them. Most cases in physics 1 and the FRQs, they'll all be combined, but really hone in on those skills that you are not confident about. Because unfortunately the physics 1 curve is not that high. It's not a good curve. So in order to get like a really good score, you do have to be confident in most of your topics. So don't cram. And I think especially like I did this for physics C2 and it did not work. Don't take a full length practice test because you're just like stuffing so much information in your brain just because of any mistakes you made or any like stress you get, that nothing's going to stay. You want to practice the stuff that you don't know. So it's like new information that you can stay. If you just practice all this random information without any direction, you can't learn anything. Okay. I'm going to hold off on the Q&A just to get to the kinetic parts. All right, next slide, please. Okay, so yeah, what is this rotational inertia nonsense over here that we've been talking about for so long? So rotational inertia the definition is that it resists, it's an object's ability to resist your change in motion, and that just depends on your mass and the shape. Oh, why is the curve bad? I don't know. I can think they think it's like algebra based, so it's a little easier. I don't think that's true, but oh well. So in linear acceleration, we know that only the mass resists the acceleration because you're not rotating. So the quantity or the object the object's properties does not play a factor in how fast you're going like linearly. But when you're rotating, of course, your shape matters. So that means in your angular motion, both your mass and the shape of your object resist angular motion. So the heavier you are, the more mass you're concentrated in that object, it doesn't want to move that fast. And that's what a rotational inertia is all about, because you don't want to your total torque is created on how fast you're going and how much your object is resisting the change in motion. So a high torque is something that has both high rotational inertia and high angular acceleration, because both are working together and increasing its abilities to create more torque. So exactly, a quantity is called a moment of inertia because it's a property of both your mass, and now you're just taking the shape into account. That's the biggest thing with rotational motion, is that you have mass, you have velocity, but that shape, which is our radius, again, that lucky R, that's what creates your difference. So thinking back to our translations, rotational inertia is analogous to mass, but again, it's a lot more complex. So exactly, the only thing you want to know is that rotational mass is based on the mass of your body and the distance your mass is from the axis of rotation. Okay, before I answer any questions, I want to show the next slide. Next slide, please. Okay, yeah, exactly. So again, write in the chat again, I will not memorize any of these equations. The only thing you're ever going to need to memorize is mr squared. And that is because sometimes you're not given any information on what your object is. They're just going to say, oh, a point mass is like 4 centimeters away from the center of rotation. That's the only thing you're going to memorize. It's also on your equation sheet, but it's just a good thing to know. That is mr squared. It's always going to be mr squared for a point mass. All of these shapes you're seeing here, you're not going to have to memorize them. It's all going to be given to you because you might be given like, oh, you have a rod about a center, a rod about the end, a hoop, a sphere, a solid cylinder. So all these shapes, the main idea that you want to understand is that all these shapes have different rotational inertia because their mass densities are different. So if you can see that apart from the point mass, the hoop here actually has the greatest rotational inertia because all of its mass is concentrated furthest away from the center. So since all the mass is concentrated exactly a distance r, which is the radius, away from the center, it doesn't have any constants or any fractions that hinder that. So it can resist the motion as it has the greatest resistance to its motion. However, if you see like the lowest one, let's see, rod about your center, right? It's such a long, thin rod, and there's so much mass that is distributed away. But there's like because the rod is so long, there's so many like tiny bits of pieces from the center that contribute to that moment of inertia as well. So since there's so many pieces that are also closer to your center, that's why the rod has a very much lesser moment of inertia than your hoop. So again, these are all different types of rotational inertias. It's honestly pointless if you're memorizing this because you will not need it. Okay, there we go. Yeah, please do not memorize these. There we go. All right, I like that. Okay, so yeah, that is mainly it. I'm gonna look if there's any questions that are specific here. Yeah, please do not memorize them. That's the main thing I want to say. Usually I don't know if they're going to be on the formula sheet. I have to check on that really quickly. But when you're just given a problem, they're also just going to say in your problem, oh, the sphere is 2/5 mr squared. You're a solid cylinder. But like someone mentioned before, you will have cases like in a multiple choice question where, for example, you have like a ramp, right? And then you have a sphere, like a solid sphere, a hoop, and then a rod, right? And they're gonna be like, or mainly it's usually, let's just go with two. Let's go with like solid sphere and a hoop around a hoop, and they're both going down a hill, right? So they're gonna be like, which one? Actually, I'll get to this later, but they're just gonna ask you to rank first of all your moment of inertia. So you'll have to know intuitively in that sense that a hoop has most of its mass concentrated. All of its mass concentrated around away from the radius, so it has more moment of inertia than a solid sphere, which has more mass density. So a lot of its mass, it's like concentrated around the sphere. So you're just gonna have to know those facts intuitively. That's why, especially like on the MCQ, you have like what 50 questions in 90 minutes. You don't want to be for one question. You don't want to be like solving like 2/5 mr squared, 1/3 mr squared to just rank it. You just want to know that, oh, okay, the solid sphere has a lot more mass, so it's more concentrated. That's why it has less moment of inertia than your hoop. Okay. Yeah, every second does count. Really important. Yeah, rod is a cylinder but skinny. So they're just gonna say a cylindrical shaped rod, etc. Okay, next slide, please. Okay, so I was so scared Zeke was gonna like talk about this topic like completely and like give it away, but I just want to bring out this like tying this topic together with this skater example because you're gonna see it a lot. So essentially, I want to ask, what are the properties that you've learned so far that are being conserved here? And now that you learned about the mass density of rotational inertia, what is changing in this as the girl grows from like putting her hands out when she's skating to like putting them together while she's skating around? What properties are changing, and what increases, what decreases? Tell me all that. Okay, I like these answers. Okay. Yeah. Right, exactly. Okay, I like this. So next transition, please. Exactly. So you guys were like, you hit the nail on the spot. Exactly. So angular momentum is conserved because we're just talking about the system of the girl and that's it. So as since she's not adding any net torque or any external force onto this, the angular momentum stays conserved. You got kind of gave away, you can see over here. So since angular momentum is conserved, we know that the values have to change a bit here. So as you see that since she's concentrating all of her mass more at the center, the rotational inertia decreases because rotational inertia likes it. It likes getting bigger when it's more concentrated out. But when you get closer, there is less rotational inertia. So since rotational inertia decreases, you guys guessed it, your angular velocity increases. Yeah, exactly. It's not the you're always going to be defined. It's always going to be defined for you what your axis of rotation is. Her axis of rotation is like her body. Like she's bringing herself closer to her body. That's her axis of rotation. And a rod, our fun pivot A, that's our axis of rotation. Whatever that is, it's going to be defined for you, and you're always measuring from there. Exactly. They're oppositely proportional, inversely proportional. And a lot of the times in physics, you're going to get these questions where something's doubled, something's quadrupled, something's halved, and how does that affect the other variables? So you have to know what variables are proportional to each other and what variables are inversely proportional to each other. Yeah, distance from the center, basically radius. Yeah. Will AP readers understand what I'm talking about if I call it? Yeah, exactly. Rotational inertia. They actually like it better if you call it rotational inertia because a lot of people just like to write I. But yeah, you can say I. I think as long as you define what you're talking about and really make it clear, then you're good. All right, next slide, please. Oh, how did the angular acceleration increase? Okay. Oops, why does it say angular acceleration? Okay, so not really in this case. So you don't, on the real answer here is like you don't know if the angular acceleration increases because all you know about angular acceleration is that the torque is equal to I alpha. So in the torque, does the torque stay the same here? I'm gonna have to think about that a little because there's nothing external being added to the torque here. Yeah, I see that. Okay, torque does say the same. Yes. Okay, so there's nothing external being added to the torque. I think that's why it says angular acceleration increases. The acceleration, the velocity is okay. I guess like the best way you can I can explain it right now. I will get back to you guys on this, but remember our equation of torque is equal to I alpha. Exactly. So I is a rotational inertia, alpha is the angular acceleration. So as of what I can conceptualize from this problem, there's no additional torque being added to the system. So our torque, similar to our conservation of our angular momentum, stays the same. So therefore, we already discussed that since she's bringing her hands closer together, the rotational inertia decreases. So similar to this angular momentum equation, our in the torque equation, our angular acceleration also increases. And if you just think about it by the definition of velocity and acceleration, since angular velocity is increasing, it's not staying constant. Since the angular velocity is increasing several steps by a certain time, there's going to be acceleration. So the acceleration will be increasing because your angular velocity is increasing. Yeah, exactly. So in this case, your angular acceleration will increase because if you think about it both mathematically, but in general, just because like Anastasia said, velocity can increase, but it doesn't necessarily mean that acceleration will increase. Yeah, that just depends on the direction where you're going. But in this case, our angular velocity is increasing by certain rates every second, so our angular acceleration does increase. Yeah, exactly. It is no additional torque. So therefore, your angular acceleration will increase by both equations. And what an angular velocity, oh no, angular velocity is not decreasing because again, this is by the property of angular momentum being conserved. So if you just think about it in that sense, you are coming closer, their mass is being more concentrated to your center. So your rotational inertia is decreasing, and therefore, since it's inversely proportional to your angular velocity, that's increasing. There is jerk. Jerk is for the derivative of force is jerk. So I'm not sure if it translates to torque, but I can look at that. Oh, sorry. Yeah. Your derivative of acceleration. I don't know if there could be jerk because your acceleration could be constant. So we can look into that. Yeah. All right. Next slide. All right. Finally. So work and energy are also gladly related in rotational motion. So the equation you're going to have to know is that, or it's also on your formula sheet, that kinetic energy is equal to 1/2 I omega squared. I is your rotational inertia, omega is your angular velocity. So oftentimes your body, a body that moves down a hill, down a ramp, wherever it's rolling, it will have both translational and rotational motion. Translational, again, is your linear motion, linear velocity, linear acceleration. Rotational is how it's turning. So just like a wheel on a bar, that means bar, not czar. But however, Newton's laws still remain valid in these problems, and that's why we can solve for them mathematically. And that's as your axis of rotation passes through the center of mass, that has to stay the same, and your rotation does not change direction. So you don't really have to worry about this in like a math problem, but maybe in an experimental problem, you do want to see if these students conducted the experiment correctly, and they did make sure to check that your rotation does not change direction in the sense that it does not go the opposite way, and the axis of rotation passes through the center of mass. So the total kinetic energy of any rigid body, remember, your rolling object has both linear and rotational kinetic energy. That is going to be equal to 1/2 I omega squared plus 1/2 mv squared. Yeah, it's another energy. So I was going to talk about this before, but I held it off for now. So if you just think about a ramp, if you just think about the ramp and any scenario, if for example the ball is just rolling down and it's not rolling down, it's just moving downwards a hill, and that it does not have any rotational energy. So therefore, we can just think about our energy unit, and therefore we can think, oh, mgh is equal to 1/2 mv squared. So that means that all our potential energy is being translated into linear kinetic energy or translational kinetic energy. However, now that if the ball is rolling as it's coming down, that means that now we've introduced rotational motion. So therefore, now it's going to be mgh, which is our potential energy, mass times gravity times height, is equal to not only just 1/2 mv squared, but it's also going to be equal to 1/2 I omega squared. And that essentially means, if you think about it theoretically, that all your potential energy is being converted into both rotational energy and kinetic energy. Therefore, your kinetic energy actually decreases when there is rotational energy, because the rotational energy takes some of that kinetic energy away. Yes, we will go into static friction into the next example really quickly. So next slide. So yeah, to our luck, the AV physics isn't that nice to us. So whenever there is friction present, it's used to convert rotational kinetic energy into linear kinetic energy. So if you just think about that for a second, your magnitude of the negative rotational work, that is basically the that negative work is friction. So that negative work is equal to the positive linear work done by the friction. So friction essentially does no net work, and I just want to, it's harder to conceptualize than to think, so I don't want to walk through an example to just go through that, and we don't have to work through that example. I just want to show how this is applied. So next slide, please. All right, so in this example, you can see that for the first part, a solid wheel of mass m and radius r move up an incline as is shown in this diagram over here. So the speed of the ring as it enters the incline is v. So you want to find how high up the incline the wheel is if the wheel slips while it goes up the incline. So slips essentially means that it's frictionless. So this ball is, we always see down the incline, but I want to show you this ball is just moving up the incline, no rotational energy. Do you guys want to solve for this, or do you want just me to go through the answers as we go? Okay. Yeah. The rolling, okay, you want to solve for it? Sounds good. Okay, so I'll give you guys like 5 minutes to solve for it. So this is just the first part, and I'll explain how the friction plays a role into this. So again, you're just using symbols. You don't really have to, there's no values here. All right, can I explain the answer, or do you guys want more time? Okay, no. So if there is if the wheel is slipped, that means essentially there is no friction. I'm saying it's all right. Next transition, please. Okay. Yes. So if you just look at conservation of energy, this is again no friction. So there's no friction. Your rotational motion will not be converted into linear motion because there's no friction for the rotational motion to resist. So this process works in the same. If you just look at we have initial kinetic energy as it moves up the ramp. So we have 1/2 mv squared, and when we reach the top of the ramp, all your kinetic energy is converted into potential energy. So you have 1/2 mv squared is equal to mgh, and therefore, if you just cancel out your masses, bring the 2 to the other side, your height of your incline is the square root of 2gh. Another hint in this problem is that there was no given like friction constant or anything, so you know that this is no friction. Why are you using linear instead of rotational formulas? Because there's no rotational motion of the wheel that's happening. If you did say that there's no slipping, that means that there is rotational motion that acts as a friction. How is h equal to h? Well, if you just simply look at the conservation of energy equation, essentially you're starting off at h equals 0, so you're starting off with no height, with just the ball moving at this velocity, and you're equaling this to when you reach the top of the incline, where you have no kinetic energy and your ball is at a rest, but essentially you've traveled that distance h. And again, this is potential energy. So potential energy is focused on the height. So if I know the angle theta is there, but if we are given the length of the incline instead of h itself, then we would have to do the length of the incline times sine theta, but we're given the value of h itself, so that's why it's that height. Yeah, that h is given in the picture. Like maybe like if it was a part, if they wanted you to go to step harder, they would have like an L for the length of the ramp, and you'd have like, for example, instead of h, you would have like L sine theta. The initial potential energy and final kinetic energy, because when you're starting off at the ramp, we're assuming that you're at height equals 0. So since there's no height, there's no potential energy. And then initially and at the top, your ball is not moving anymore when you reach the top of the ramp. So therefore you don't have any movement. So if you don't have any velocity, your final kinetic energy is 0. Oh, the velocity didn't disappear. Just it's not written out, but it's just saying that you're. Oh wait, hold up. Ooh, wait. Okay. I see what you guys are saying. Okay. Yes. Yeah, it was your algebra. It was algebra. My bad. Okay, yes. Okay, I apologize for that. You guys are right. Okay, so I will, this was like my teacher's notes that I had used to help for the friction explanation, but you guys are right in that sense. So the math was not right in this. Okay, so it does not seem that it's like that for the other part of the problem. So what you guys had is correct. So your H would be equal to 1/2 v squared over the gravity. Yes, my bad. I apologies. Okay, next slide, please. I hope you guys it look like you understand the concept better than I did. So yes. All right. Next slide. Okay. So in this case, wow, that was my brain just died. All right. Okay, next slide. I think this was still the previous slide.
All right, I'm just changing the format of the next slide so you don't get any spoilers, guys.
Okay, thank you. Now I'm just going to look at the other slide just to make sure that there's no incorrect math in there. Okay, yes. Hopefully that is right. If you guys catch on something, that's an extra point on you guys. Thank you. All right. Okay. Oh, wow. Okay. That is a W transition, Juliana. Okay. So now you find out how you have to, so now we have friction is present because there's no slipping of the wheel. So you want to find out now, calculate the new height up the incline as the wheel goes. So essentially, I will explain this in detail on what this means, but you want to think that if there is friction, then the rotation, the rotation of the wheel, that rotational kinetic energy helps it move forward. So that friction is the rotational kinetic energy, and that's what helps it move forward, which actually counteracts the linear kinetic energy. So therefore, you're going to have to think that both the rotational energy and kinetic energy are working together in order to move that ball up the ramp. So just take a few seconds to follow this, do this, calculate this out. Would you just replace the kinetic energy with rotational, or would you use both? Okay, yeah, so this is, you're still moving, so there's still velocity. So that means you can't cancel out the kinetic energy. However, since there is no slipping here, there will be rotational kinetic energy, which acts as the friction, so it could move up. Oh yeah, no, Juliana, literally same. Okay. In the meantime, I'm gonna change the slides a bit and send a little note to my teacher that the math really didn't work and I didn't look at that. All right. No, so you don't include any I or W in your equation. I don't want to do that in the final answer. But you should only have your velocity and any physical constant like gravity. Oh, it is a solid wheel, so the rotational inertia of the solid wheel is 1/2 mr squared in this scenario. Yeah. No, it's not a point mass. So it will not be mr squared. So you're gonna have 1/2 mr squared is going to be your rotational inertia. Yeah, some of you guys already had that. Thank you. Yeah, they'll tell you so on the exam. I'm just gonna go check the physics 1 reference sheet again if they have it on your sheet itself. But in that example itself, you should have it. Okay, on your reference sheet, it does not look like you have like a bunch of shapes and they're gonna tell you the rotational inertia. So in that context of the problem, they'll say the rotational inertia of like a sphere is 2/5. Okay. All right. I think, do you want me to move on or do you guys want to wait a bit? What would happen if you put 2/5 instead of 1/2? So 2/5, your answer would be different because since you're just dealing, the fraction does cause like, how do I say it? So when you sum your fractions together, because when you're converting between your inertia to your to the formula of what 2/5 mr squared, your overall answer would be different. Okay. I will continue. Okay, yeah. That is, wow, my cousin actually calls me Shogun, so that is something which I didn't want to get out in the public, but all right. Thanks for figuring that out. Okay. I think we can move on and reveal the rectangle, which by the way, it was Juliana who did that because I actually had the answer full out in the open. No worries. It's all good. All right. Next transition. Is it working? Okay, there we go. So yeah, you guys do have the right answer, or I had the right answer this time. The height is 3v squared over 4g. So I just want to get this out and say in the open. I'm talking about friction and I'm putting in parentheses friction present, but I didn't give you any like coefficient of friction, or I didn't give you, the force of friction is this. So that means that you have to think about this intuitively, that when there's friction and there's no slipping, that means as the ball is going up the ramp, that means that the rotation of your wheel helps that ball move forward, because again, your velocity is moving forward, but as you're rolling, that means that you need that friction itself is that rotational kinetic energy. So you don't need to add any additional friction constants, or some people I saw before when they did this problem in class, we added like a mu in, but that's not related to the problem. We're just saying that our rotational kinetic energy is that friction, that helps it move forward. So therefore, your equation will now be your total kinetic energy is 1/2 mv squared plus 1/2 iw squared, or I omega squared, why did I say w, is equal to mgh. And therefore, so like we had before, the 1/2 mv squared stays. And now remember, you can convert any time from linear to rotational. So your I didn't give it to you before, but you guys figured that out before I did actually, it's 1/2 mr squared for your solid wheel. And then your omega is equal to V over R. So therefore you substitute V over R for omega, and you square that is equal to all the potential energy, which is mass mgh. So therefore, if you do the whole constants again, this is the thing where I think, Ben, you were saying that if I use 2/5 would it be different? So yeah, here it would be different because when you're multiplying your constants and all that, it does become out to be different numbers. So you do have 1/2. So yeah, I cancel out the m's first. So it's 1/2 v squared plus 1/4 v squared is equal to gh. And then 3/4 of v squared is equal to gh. So your total height is 3v squared over g. Now, this problem because we're going up the ramp, that's why I called it as friction. However, if your ball is if you have a ball going down the ramp, then it's actually the same thing, because if you think about it, you're starting off the ball with all your potential energy. So you have mgh, and as you're rolling down the incline, you have both rotational kinetic energy because you're rolling down the incline, and then you have kinetic energy because you're moving down at a speed. So you're still going to have all your potential energy is equal to the rotational kinetic energy plus the initial plus the kinetic energy. All right. When there is friction, we use kinetic energy equation that involves momentum of inertia and angular velocity. Well, in this scenario, again, you can't, I wouldn't say don't memorize every type of scenario again. In this scenario, it clearly says there's friction is present, and we're not given any other information about friction. So yes, we can assume that rotational inertia of the wheel helps that ball move forward. Oh, if you did it a different way, that is solid. Yes, exactly. The friction does act as a torque as it's like perpendicular to your center of gravity. Okay. Well, yeah, you guys are solid with these explanations in the chat. What did you substitute for rotational velocity? So for omega, if you check on your equation sheet, velocity is equal to the radius times omega. So omega is equal to velocity over the radius. So you just substitute that in as omega. And then since omega is squared, you have v squared over h squared as your radius. Yeah, it'll tell you if the wheel's inertia is 1/2 mv squared. Okay, so this was a lot of talking and a lot of practice problems. So I think we can take a break for now until we get to the next part, because the next part is going to be all just MCQs and FRQs. So I'll be still online in the chat just to answer any questions, because that question is a little trippy. But then we can take like a good 5-minute break for you guys to stretch before we do the next problem. All right. And yeah, we're going to be on the chat just looking at questions.
All right, hello guys, we are back and we have a practice MCQ for you. So work on solving that and then type in the chat when you're done. I'll put up a poll for the answers. If it's a little blurry, it should be in the slides in the Cram Hub. This is slide, let me check. This is slide 29. All right, is everyone ready, or should I give you guys some more time? Okay, I think people are ready. So the first thing that I saw most people do is a lot of people picked A because they said, okay, torque is going to be force times distance times sine of the angle, right? But the problem is they're actually going to give you the wrong angle here, and I will show you why. So here I drew like a free body diagram of where mg would be located. And notice here that mg isn't actually located at L. It's located at L divided by 2 because gravity always acts at the center of mass. So it would act right at the middle of the ladder. So the first thing you have to notice is that distance is going to actually be L2. And then the second thing you notice is that the part of gravity that will equal the torque will be the T line that I've outlined here. And then I also outlined the angle that's inside the triangle made by T, the ladder, and mg. And since A, theta, and mg are like part of a right triangle, that means A equals 90 degrees minus theta. So sine of A equals cosine of theta. And that's just going to be a trigonometric rule. And then the force of gravity or weight will just be mg. As I said earlier, gravity acts on the center of mass, which will be L2 in this case, because we're assuming that the ladder is uniform, which means that the mass is evenly spread out. And then, as we said earlier, only the perpendicular component T is a part of torque. So that means that sine of A equals T over mg, because that's going to be opposite over hypotenuse. So T, which is the only component that's a part of torque, is equal to mg sine of A or mg cosine of theta. So torque would be this T times the distance. So that would be option D, which is mgl cosine theta over 2. D is correct, not A. A is if you are quickly going through this problem and just going to plug it into the formula, but you really have to look at the problem and draw the diagram to see which angle is correct and where the force is located to get D. Yeah, this was a tough one. Does anyone have any questions about how I found that? Okay, it's cosine because if you see here, I'm going to be using this angle that I labeled A because it's actually inside the T and G like triangle and it's easier for me. So here the opposite side would be T, which is the perpendicular part of the force, and the hypotenuse is mg. So opposite over hypotenuse is sine. So over here you can see sine of A is T divided by mg. So T equals mg times sine of A. And earlier we know that A plus theta plus 90 degrees makes 180 because they're part of this bigger triangle made by mg, the floor, and L, which is the ladder. So A equals 90 minus theta. So sine of A equals cosine of theta, which is just going to have to be a trigonometric identity that you need to know. These questions are kind of rare, but they do pop up. What was the formula again using for torque? The formula is the force of gravity times the distance times the angle. But I simplified force of gravity times angle to T because that is the perpendicular part of F of T. Yeah, the angle is tricky in this one. All right, does anyone have any more questions? Yeah, Sherry, it depends on which angle you're given. it's going to typically be sine of theta, but if you're given the opposite angle, then it's going to be cosine, and you have to figure out which one it is. Yeah, the trick is to draw the component that is perpendicular to the ladder. And I know some of you asked about like normal force from the wall earlier, but the problem was just asking from the torque due to weight, so we're not going to take those into account. All right, I'm not seeing any more questions, so are we all set to move on? I think we're all good. I'll move on to the next slide. Via cosine is adjacent over hypotenuse, and sine is opposite over hypotenuse. All right, I'll give you guys some time to work on this problem. Okay, is everyone ready? I think most people have answered. So the correct answer here is C. So the options here were A was the mass of the rod, since it's related to the force exerted. B is the length of the rod, since it's related to the rod's rotational inertia. C is the average torque, because it's related to the change in angular velocity. And D is the average net force applied. So first of all, you see that the problem here is asking for a quantity that will change angular momentum. So you can immediately go cross off A and D, because mass and force are both translational topics, and they're not going to really change the angular momentum. They're not the correct words or variables to use. So we have a choice between B and C. B is the length of the rod, which is related to inertia, rotational inertia, and C is the average torque. So the answer here is C, because if you look back, angular momentum is changed by torque and time. Just as momentum is changed through force and time, angular momentum is changed through the angular equivalents, which are torque and also time. Here, the length of the rod would not have any effect on the angular momentum, as it would remain constant throughout. So that inertia, that rotational inertia would remain constant. So it's not really something you have to measure. What would actually change the angular momentum is the net torque, because that would change the angular velocity. And angular momentum is mass times the velocity times r, or a moment of inertia times angular velocity. All right, I think most of you got that question. So we will be moving on, unless anyone has any questions. I'm not seeing any questions, so I guess we'll move on.
All right, okay, we have a very fun FRQ MCQ here. All right, so just take it step by step. There's a lot of information I'm going to brain dump at you, but let's get started. So a cart with a toy projectile launcher attached to its top travels forward at a constant speed v initial. The launcher fires a solid sphere forward at a speed much greater than that of the cart launcher system. The cart's speed after firing the dart is v final is less than v initial. Frictional forces are considered to be negligible. So which of the following scenarios best represents the rotational analog to the situation? Remember how you guys were making fun of me for saying analogous? Here's a word. So A, a gaseous planet rotates with a large rotational velocity, causing the middle of the planet's equator to bulge outward. B, a spinning platform falls onto a stationary platform. Both platforms rotate together, but at a smaller common rotational speed than that of the spinning platform immediately before the collision. C, a child on the edge of a large rotating disc throws a ball in the same direction as the child's tangential velocity. And D, a figure skater spins with the skater's hands at the skater's waist. When the skater extends the skater's arms outward, the skater's rotational velocity decreases. That's valid. Okay. Oh, thank you, Juliana. I always forget to do the poll. Ooh, okay. There's some conflict. I see A, C, D, a few Bs. All right, interesting. I see like a steady. Oh, okay. Wow. I see a lot of C's now. All right. Wow. That was like a dramatic flip. All right. Okay. So I think a lot of you guys, I don't see anything in the chat right now. So I think we can move on to the next slide. Okay, so yeah, you guys were right for C. So this is a very theory heavy question and there's a lot of like brain dump, but essentially the way how College Board explains this, since this is a College Board question, is that you have to think. I drew this very beautiful diagram over here, which I'll explain in a second. I don't know if you can see because of the light, but essentially you want to think, let me see, okay, that's not going to work. So essentially you want to think the child, disc, and the ball originally rotate together with the same angular velocity. So therefore we want to say that the child, disc, and ball system conserves angular momentum. So after the child throws a ball forward, the angular momentum of this entire ball child disc system will not change. However, if we break apart our systems into two, can you guys see me? Okay, let me know. It looks like you. Okay. Whoa, I did not know that was happening. I was just talking, and then all right. Okay, so let me just restart. So essentially, you want to think this. Okay. All right. So essentially, the child, disc, and the ball, you want to think of it as one big system. So if we just think about it as that system, specifically, that the angular momentum does not change for that system. However, if we break apart those two systems into different portions, so if I just think the cart and the launcher as one system, and my ball as another system, all right? So two different systems now. So since we know that when we launch the ball will increase in speed at a much faster speed, but the final velocity of our launcher and our cart decreases. So therefore, we're going to say that the linear momentum for our launcher and cart system does not decreases because we're losing that energy, and V final is less than V initial, and our ball here is increasing in linear momentum. So analogously, now we're going to think about angular momentum. So in this child disc system, child, disc, and ball system. So we're going to think about this again, we're going to make it exactly analogous to what we just talked about. Child, disc, and ball system, angular momentum does not change for that. But now let's break it apart into two. So now we have our child and disc system. So in our child and disc system, essentially we're at this large rotating disc, but then when the child throws the ball is gaining in angular momentum because it's increasing in speed, but the child and disc system decreases in angular momentum because it loses that speed. So therefore, if you guys know my drawing, okay, so this is a very gorgeous drawing. I should think about my new major as like an artist or something, but I want to show you that this is our launcher and this is our ball and this is our cart. That is equal to our child, disc, and ball. Linear momentum, linear or angular momentum here is conserved. Then here, this is our thank you. This is our cart and our launcher, and this is our child and our disc. So here we are losing. Ooh, it's backwards, but it's okay. Thank you. I appreciate it. So here we're losing speed. So therefore, the momentum is not conserved. This is only for when we're breaking down the systems. Remember, the entire system, we're conserving it. And now finally, this is my child ball and the launcher ball. So here we're gaining in speed. So therefore, you see how everything is like equal. That's all analogous. So that's what these questions are really asking you to think that, okay, what is similar to what? So a lot of you guys got that. I actually had to think about this for like 20 minutes straight. And I was like, okay, what am I doing? And then you have to think about the different velocities. I really appreciate the positive comments on my drawing. My sister does not. So thank you for that. But yeah, good job. Thank you. All right, we can go on to the next question unless there's any slides. And any slides, any questions? All right, okay. Next question. Whew. So a uniform cylinder of radius r, mass m, and rotational inertia I initial is initially at rest. The cylinder is mounted so that it is free to rotate with negligible friction about an axle that is orientated to the center of the cylinder and perpendicular to the page. A light string is wrapped around the cylinder. At time t equals 0, the string is pulled with a constant force F initial, which causes the cylinder to rotate, as shown in the figure. After time t equals t final, the string is completely unwound from the cylinder and loses contact with it. If necessary, how can a student determine the change in angular momentum of the cylinder from time t equals 0 and t equals in final? All right, 17, 1, 2. Okay, I don't see any change in the poll, so I think I will move on. Next slide, please. All right, yeah, you guys are pretty good, like really good at these theoretical FRQs, but you were right. So if you think back to impulse, it's funny, there's actually no such thing called angular impulse. Like it's not like a definitive term, but we like to use it. So you want to, so essentially if you just think about the change in angular momentum, remember angular momentum is the rotational inertia times angular velocity, IW. But so change in angular momentum is, if you think about to the linear momentum formula, the change in angular momentum is equal to the final angular momentum minus the initial linear momentum. So unless if you know like the initial velocity, the initial angular velocity and that you don't know how to actually solve the problem by just doing that by using torque is equal to I alpha. So the only way if you do it, if you think back to the formula for impulse, that is what? It's force times time, right? So if you think about it, again, analogously in the angular formula, you can see angular impulse is equal to torque, which is essentially analogous to force. And you want to see essentially how torque is changing over time, right? So so torque is equal to, remember, it's RF sine theta. And since the force is exactly, it's 90 degrees, it forms a perpendicular angle with our torque, our axis of rotation. We can simply multiply the radius times F, and we multiply by R because the radius is the distance the force is from, there's a perpendicular distance the force is from the axis of rotation. So then you're simply just doing rotation, the radius times the force times the change in time. Remember, we're given that the change in time initially is 0, and then that time we're given is t final, or they voted t initial, but I thought that was confusing. So our answer is B, which is the you calculate the radius and you multiply the radius times the force times the time to get your angular impulse. All right. Let's move on to the next slide. This should be the last MCQ, and then Juliana has a really fun FRQ for you guys. All right, so that's another practice question. We're on a roll because it's like a roll, it's like a disc. That was pretty funny. So two small objects of mass M initial and a rotating platform of radius R and rotational inertia are about its center composed of a single system. Okay, I got a laugh. There we go. So students use the system to conduct 2 experiments. Another experimental question, the objects are assumed to be point masses. I should major in comedy and art. That's a good suggestion. So each object of mass M initial is placed a distance R1 away from the center of the platform, such that both masses are connected on opposite sides of the platform. So you guys can't see it, but those really tiny words, the image on the left is experiment 1, the image on the right is experiment 2. So a constant tangential force FO is applied to the edge of the platform for a time t. The system is initially at rest. So consider both experiments. How do the angular momentum of each system, L1 and L2, and the angular speed of each system, omega 1 and omega 2, compare after time t? And you have A, B, C, D over here. Okay, I see a few ABs and ooh, okay. How it's like ever changing. We'll just see how like the poll changes. But yeah, I see mostly B's, a few D's, and then like A's. All right, let me know when you want me to move on. Okay, ooh, okay, 26 votes for B. Nice. All right, let's move on to the next slide. Okay, all right, and the answer is B. You guys stayed on a roll, so that's great. So this is like very similar to our skater problem. So the funny thing is they give you so much information for no reason. Like honestly, the way how whenever I'm given those like FRQ of MCQ problems where you're given so much like information and like your head is spinning like how do I get started, and you're given diagrams or graphs or anything, the first thing you want to do is first read the question, and then first look at the graphs or the diagrams, then read the question. Because what happens is that if you just go into a problem and just read all that like blurbs of information, your brain starts like panicking subconsciously and it starts spiraling because you took in so much information and you don't know what to use. So if you look at the question if you look at the graphs or any diagrams first, and then your brain starts to get like a subconscious thing, okay, I see like mass and radius is smaller over here, but it's bigger over here. Maybe they're asking something about like conservation of angular momentum or like how something's changing. And then you look at the question, and you're like, okay, this confirms or denies what I'm asking for. Then you go back to read the blurb, because when you're looking at the blurb and you're reading it with like a focused mind, then you're thinking, oh, okay, I have to look for these keywords, maybe angular momentum. Then you can actually like process and strategize the information, because all the information about like the pulley, like the force and everything, that had nothing to do with the actual course, the problem. So if you think about this idea, essentially, if you looked at the two graphs that we had for the first disk, we had like a longer radius, and the second one we had the radius shorten over here. Now, since the radius shortened, that means that our rotational inertia shortened. However, these are two disks, and we're treating the disk as a whole system. So that means nothing changed. There's no external torque or anything. So angular momentum is conserved between both of them. Usually it's always conserved unless there's some additional torque. So therefore, you can already eliminate two of the answers, which says that, oh, angular momentum is different. Now you just have to think about in what way. So the angular momentum in the rotational inertia for the second disk decreases. So therefore, in order to maintain angular momentum, the angular velocity for the second disk has to increase. And you guys got that right as B. Great job. All right. Okay. So I will be handing it over to Juliana now for the FRQ. And then hopefully if we have time after the FRQ, Tammy will be leading a simple harmonic motion quiz just to review that topic from yesterday. If not, that's all. We're all saving that for our cram finale. All right. Okay. Next slide. And Juliana, it's all yours.
Hello, everyone. Can everyone read this slide? Having any issues? Oh, good for you, AP class study. All right, just in case you can't read it, I will read it out loud for you. So it says the left end of a rod of length D and rotational inertia I is attached to a frictionless horizontal surface by a frictionless pivot at the far left as shown above. Point C marks the center of the rod. The rod is initially motionless but is free to rotate around the pivot. A student will slide a disk of mass M disk toward the rod with velocity VO perpendicular to the rod, and the disk will stick to the rod at a distance x from the pivot. The student wants the rod disk system to end up with as much angular speed as possible. And then suppose the rod is much more massive than the disk, To give the rod as much angular speed as possible, should the student make the disc hit the rod to the left of point C, at point C, or to the right, and justify your answer without using equations? All right, when you're all set, type your answer in the chat. Okay, are most people done, or do we need a little more time? Okay, so I'm seeing that most people have given answers, so, oh, more time? Okay, I'll give you a couple more minutes. I guess we'll go through one playthrough of Samosa. It is slide 37. Okay, I think that's enough time for most people, so the correct answer is to the right. The explanation I went with was that torque is directly related to distance. So a greater distance equals a greater torque, and a greater torque increases the final angular speed. So farther distance equals greater torque equals more angular speed. You could also tackle this problem using angular momentum and say that if the disk is farther away, it has a larger initial angular momentum. So the final system will have a larger angular speed. But it doesn't really matter which explanation you use as long as you exhibit a correct dependence on variables. All right, so part B. On the internet, a student finds the following equation for the post-collision angular speed of the rod in this situation listed here. Regardless of whether this equation is correct, does it agree with your qualitative reasoning in part A? In other words, does this equation for W or omega have the expected dependence as reasoned in part A? All right, and then I'll give you a little time to solve that and write your justification. Okay, is everyone done, or should we have a little more time? Okay, it looks like everyone is done, so we'll move on to the answer. And the answer is yes, this is reasonable because speed increases as the disk is farther from the pivot or heavier and decreases as the moment of inertia, resistance to angular movement increases. This agrees with reasoning in part A, where distance from pivot and angular speed are directly related. I guess that cut off in the answer. But basically for this question, all you have to mention is that the equation does show a direct relationship between angular speed and displacement, since that's what they asked in part A. and that will get you all the points that you need. So just make sure that you do address part A in your answer. All right, so part C. Another student comes deriving an equation, makes a mistake, and comes up with this equation. Without deriving the correct equation, how can you tell that this equation is not possible and that it doesn't make physical sense? Briefly explain your reasoning. Okay, so it looks like most people are done. So I will reveal the answer. And it says this equation is not possible because it says that I, or moment of inertia, increases, the angular speed increases since I is in the numerator. Moment of inertia resists angular acceleration, so a larger I would mean a slower final speed. And for this equation, you could either tackle moment of inertia and say that it is in the numerator when it's supposed to be in the denominator, or you can talk about the mass of the disk and say that it's supposed to be in the numerator and instead it's in the denominator. So you can talk about one or the other or both, although I do recommend only tackling one on the test because that is enough to get you all of the points and you don't really have the time. Okay, does anyone have any questions for this one? Andrew, you could say that, but it would not really be enough to get you the point because it doesn't talk about an impossibility in this equation. Samosa, yeah, indirectly proportional should be okay if you're talking about a moment of inertia. Okay, any more questions? Okay, I'm not seeing any, so let's move on. We didn't do the transition for this one, huh? Okay, I'm going to come up with another mysterious curtain for you guys. Okay, this should be correct now. Pretend you didn't see anything. Use samosa to clear your brain. All right, I'll give you some time to solve this. Okay, I see a couple dones and we're running out of time, so I'll just get started with the explanation. So the easiest way to solve this problem is through the conservation of angular momentum. So the angular momentum at the beginning, which is just going to be the angular momentum of the disk since it's the only thing moving, should also equal the angular momentum of the disk plus rod once they're stuck together. So we're told here in the problem that the angular momentum of the disk is m disk times VO times x. And then this should equal the angular momentum of the disk plus the rod. So if you remember, the equation for angular momentum is total inertia times total angular velocity. So on the left here, you have the total inertia of both items, which is I plus m disk times x squared. And both of these constants are given earlier. At the first sentence, you can see that the rod's rotational inertia is I, and in problem D, it's given that the rotational inertia of the disk is m disk x squared. And then you're going to multiply that by the final angular velocity. So you would divide both sides by the final inertia to get that the final velocity is m disk times VO times x divided by the final moment of inertia, which is I plus m disk x squared. So yeah, a lot of people probably overcomplicated the problem, but it's really only an angular momentum problem. So here the clue is they give you the angular momentum outright, and they're asking for the speed of the rod. And also this is a collision, which is a hint that it's going to be a momentum problem. So right now we're just about running out of time. So before you go, please click the green button below and take our AP Physics Night 4 survey, and we will see you tomorrow for the grand finale. We will cover anything that we didn't get to and anything that you may have missed from yesterday. Oh, angular momentum of the rod, it's of the rod plus disk. The I comes from the first sentence. Oh, you add mx squared and I because you want the total moment of inertia. I is the inertia of the rod, which is given to you in the first sentence, and mx squared is the moment of inertia for the disk, which is given in 1, 2, 3, 4, the fifth line. So both of them are just given to you. All right, we have to end it here, so I guess we'll see everyone.